Welcome to this talk. The outline of this talk includes 4 parts. So, in our deep sparse conformer, we first describe the motivation. The second includes 2 improvements to use sparser attention to make the training and inference of our deep sparse conformer to be faster. The second is use a deep normalization technique to build as deep as 100 layers of the encoder. We then describe experiments and conclusions. So let's briefly recall the original conformer proposed by Google researchers 2 years before. The right-hand side figure is taken from this paper. It's a used Macaron architecture with 2 feed-forward modules, this and this. And inside this 2 feed-forward module, there is a convolution module that tries to capture the local features of the input wave, and also a multi-head self-attention module that tries to capture the global information of context of the input. And it has achieved state-of-the-art accuracies for a lot of languages of ASR, even using large-scale training data set. Still, we have 2 questions. The first one is that, as you know, using self-attention is relatively slow at processing relatively long waves of computing and memory usage. And we want to some sparse attention and without lose accuracy. The second one is that we are wondering if the deep architecture is helpful to the accuracy, for example, from 18 to 50 or even 100 layers. So then we come to our new architecture. We name it Deep Sparse Conformer. We have 2 main updates. The first one is use sparse attention. So that changes the L square complexity into L times log L. L is the number of frames or the wave lines of the input. The second one is to use a deep normalization to extend the encoder layers from 18 to as long as 100. So sparse attention is proposed. We currently use the probe sparse idea proposed by Informer in III last year. So the major idea is that we are trying to not use all the queries to compute the attention score, but only a number of it, so log L number of it. We need a ranking mechanism, a ranking measurement that tries to give us a hint of which query vector is the most important to compute the attention matrix. And the algorithm is very simple. We first randomly select a subset of K, and this subset of K will be used to compute the measurement. This measurement includes 2 parts. The first one is a max score of K, Q, and query, and K, QI, and KJ, and then minus the mean score of the query and K. So basically, this leverages idea we are trying to make the distance of max and mean to be as light as possible. And after we compute the measurement of every query, we actually compute the attention, the equation 7 to finally obtain the attention matrix of between Q and K. So this actually gives us a hint that we can make the things to be quicker. And in our paper, we actually describe an algorithm with 5 important parts. The first thing is that it uses the linear projection layers, 4 layers, to respectively project the query, key, value, and position into tensors. And after that, we pick a subset of keys to compute the query measurement. So this is subset key part. And when we compute the importance of the queries, we take all the query into consideration. So here is actually L number here and the log L number here. After we have this measurement, we pick the top log L number of queries to finally compute the attention score. So every step we actually maximum use L times log L as a upper bound time complexity. So through this way, we are successfully built a model that uses sparse attention. And the second idea is deep normalization. We borrowed this idea from the DeepNight, which is proposed by Microsoft researchers this March. So they successfully use this idea, build a 1,000 layer transformer for machine translation. The background is very simple. So we have two types of layer normalization. So pre-normalization and post-normalization. So different positions of layer normalization. So the good thing of this pre is that it's fast, but unstable. And for post, it's slow, relatively slow, but it's good. Result can be achieved. So used in transform. And this deep normalization idea is a kind of combination, balance the good things of pre-Aaron and post-Aaron, and they use a number of encoder and decoder layers to compute something like a hyperparameter here, alpha. And when we do this residual connection, we use alpha to weight x, and then use post-Aaron here. And its implementation is very simple. We exactly borrow the idea of DeepNight, and since our ASR model is an encoder-decoder model, we have several encoder layers and several decoder layers. So N here is stand for the encoder layer, number of encoder layer, and M stand for number of decoder layer. So it's very simple. We simply use the last row of this table and compute the encoder and decoder beta hyperparameters during the connection of the self-attention and FFN during the residual connection. So as a very brief survey, we have two major updates: use the sparse attention and use the deep normalization to do this. And we briefly change the two equations. So here is a change, so the layer normalization, the second change, with alpha 1 to alpha 4, which are functions computed by the encoder and decoder layers. Okay, we talk about experiment. So our experiment is based on VNight, which is open source ASR model, achieves good industry level ASR accuracies. And our update code, we also put it in GitHub. So here. And for training, we actually use two losses, CDC loss together with the attention loss. Since we use transformer decoder here, and we use two directions, left to right and right to left, we use a linear combination of the three losses to compute the final loss. So during inference, we actually use the CDC beam search together with attention rescoring. So we briefly talk about the training detail. So we have an encoder of the wave, and we have a linear projection from the 500, for example, 512 encoder dimension, hidden dimension to the vocabulary size, and then we compute the CDC loss. At the same time, we use the output tensor of encoder and send it to the transformer decoder, so that it can actually give us two losses, KL divergence loss. We see a detailed example here. So for the left to right decoder, the input is a reference ABC, and the decoder's input, we put a start of sequence here, and then we use the decoder together with the memory as an assistant. We use cross attention here, and also we compare the reference with the output of the decoder using the KL divergence loss. So quite similar for right to left decoder, we actually revert the input sequence from ABC to CBA and insert start of sequence at the beginning. We actually predict the same thing, ABC with end of sequence. And also we compare these two sequences. This is a reference. This is a model output prediction and compute the KL divergence loss. These three losses, CDC, 2, KL divergence loss, will be linearly combined together. And the inference is quite similar. So basically, we have a wave input. We use the encoder and linear prediction. So we have a unbiased output hypothesis by the CDC beam search. And the output, every hypothesis will be sent to the bidirectional decoder. This is a non-autoregressive decoder since we only do the inference once. So we do not generate the output step by step, but we only give one shot output. So we have the two scores of two decoders, and then we reweight the score hypothesis ABC by the same hyperparameter. Yeah, PDC score, left-right score, and right-left score. Okay, we come to our major result. So we use the CSG Japanese 500-hour ASR dataset. So with the same parameter size, 175 will directly compare with the strongest baseline conformer. We also compare with the transformer, ESP-NIGHT conformer, and the CITRI-NIGHT, which is a pure CUM model. So we can see that we compare the conformer with our this sparse conformer with the same model size. We can achieve relatively better CR, and the speed of inference is 1.23 times faster, and also the training time is only 80% per epoch for training. Another question wondering is that is a deep model can achieve a better result? So we found that it's not exactly the same way. So when we see the model is small, the CI is the worst. But in the middle size, we can achieve the best CR on the test site. When we enlarge from 12 to 17, 50, and 100, actually the CR slightly drops. And actually they are all slightly better than the conformer large model from the Google baseline. So it's stable, possibly in the future when we use this sparse conformer for training the unsupervised wave-to-vec models. And yeah, so basically we assemble the several models together from small size to middle size and to large size, and we see that the accuracy the CR drops slightly. So basically we think that a deeper model can bring diversities to the search space. So in the future, possibly we can use this idea for self-training. And to conclude this talk, we actually propose two updates for the conformer, sparse attention, and deep normalization. So for direct comparison with similar parameter size, we can achieve a better result of CER and least training time and quicker inference speed. So our code is open, so we appreciate if you can have a check and train our model in other languages. So we support sentence piece and character level models. That's it. Thank you very much for your attention.